to this video. Today I will be talking about application of Holevo-Hellstrom theorem in subchannel discrimination task. So this will be based on a paper Operational Advantage of Quantum Resources in Subchannel Discrimination by R. Takagi and others. So it will basically show how Holevo-Hellstrom can be applied in simple scenarios with channels. So what we have is, suppose we have a black box which has two channels in it, epsilon 1, or let me call it epsilon 0, and we have epsilon 1, and there is an entity in the box who applies this channel to any input state row with half probability. So basically we have half epsilon 0, sometimes epsilon 0 is applied, and half epsilon 1, sometimes epsilon 1 is applied. And then this initial state is like a probe state. And what happens is this entity gives the output some state row tilde, which is after applied this channel. And our task is to maximize the guessing probability. So we measure this output state with some optimal POVM M0, M1. And the task is to maximize the success probability of guessing. So probability of success of a state row is given by, so it is defined as, so with probability half, the channel applied is epsilon 0, and I also measure that. So that is trace of epsilon 0 of row times M0 plus half trace of epsilon 1 of row times M1. So this is can be written as summation over I, Pi, expectation value of epsilon I row with Mi. So this is the inner product here, and the idea is to maximize this probability of success. And here you can see that Holevo-Hellstrom will have an important say. But we will try to talk about convex sets and how this kind of game can help to ascertain the resource content of states. So in this, convex sets plays an important role. So the entire set of density matrices I can denote by D, and in this we can have a convex set. We call this set as F, and this is also called free states, and this state is convex and closed. So convexity simply means that if rho and sigma belongs to the free state, so if rho belongs to F, sigma belongs to F, then this implies P rho plus 1 minus P sigma belongs to F. And closedness means that certain sequences in the free states, they converge to a free state. So when I say free state, it is the state inside the convex set. And suppose I have a state outside this row, what I can say is that this state which is outside, this state is helpful in certain discrimination task. So this is the main idea. So what we have is these discrimination tasks helping us ascertain whether a state is inside the convex set or outside the convex set. Now where does convexity come up? So convexity comes up in many scenarios in quantum information theory that I will discuss now. So convexity. So let's discuss the scenarios. The first scenario is the well-known entanglement case. So if you have entanglement, we know that there is entanglement between two parties A and B. Then the set of states which are separable forms a convex set. So separable states can be written as the separable states can be written as SEP AB, and they are convex hull. So all the possible convex combination of states which are uncorrelated. So this convex hull itself means that it forms a convex set. So there is also another way to write the separable states. It is similar or equivalent. It is summation over I, Pi, rho I, tensor sigma I, where sigma is on B part and rho is on A part. So the second scenario where convexity plays an important role is when we talk about the theory of asymmetry. So basically, what is asymmetry? It is kind of quantification of symmetry breaking with respect to some given symmetry group. So suppose we have a group G and it has some unitary representation, G goes to U of G, which is a unitary matrix, and then we can call the set of symmetric operators under this group G, or the set of symmetric density matrices, as defined as sigma, such that UG sigma UG dagger is sigma. So it is symmetric for all G belonging to G. Now it is easy to see that this is also a convex set. This is a convex set. This is a convex set, and this very well can be our free states that I have shown here. So these are like examples. So this state can be the free state F here, and I can have an asymmetric state which lies outside this. Then I can have a third category. The third category can be the states which lack coherence, and it is related to this symmetry breaking. For example, under, so let's write it down first, coherence. So under U1 symmetry of some non-degenerate Hamiltonian, so consider SG under U1 symmetry. So symmetry. Consider SG under U1 symmetry of Hamiltonian H, which is of the form of lambda I. So this is non-degenerate. To avoid coherence sectors, like you can have incoherent sectors which are block diagonal appearing. But the main idea is now states which will be of the form of sigma equal to summation over I pi II. So basically diagonal in the basis of this non-degenerate Hamiltonian, they basically will be a symmetry under e power IHT, if you think. So these kind of states are called incoherent states, incoherent, and they are also convex. Set. Further, there is another example which is very useful. It is in quantum thermodynamics, where you have the Gibbs state, which is a single state, which is a convex state, because it is just a single point. Then you have example from quantum computation, where what you have is basically convex hull of phi I states, such that the state phi I is generated from the Clifford group acting on the zero state. So basically Clifford groups are set of quantum circuits which are classically efficiently simulated, can be classically efficiently simulated. And these group, for example, you have Hadamard gate, you can have C0 gate, these forms Clifford group, and you can have a Clifford gate acting on the zero state, which is the set of like the ground state, and you can get a state which is a stabilizer state, and convex hull of these stabilizer states forms the stabilizer set of states STAB, and any state outside this is said to possess magic, and this, because I have a convex hull, is also a convex set. So basically the idea is I can have a lot of different sets which are convex, and I can talk about a state outside this convex set. So now the main idea is to try to ascertain some usefulness to this state outside this convex set. So what is the main theorem? I will mark it with red. Main theorem. It says that rho does not belong to a convex set if and only if. So this is important. It says that rho does not belong to a convex set. So I put a does not belong to sign. If and only if max over all possible measurement strategies, max of this PS of rho is greater than max sigma belonging to F mi PS of sigma. So the main theorem is that rho does not belong to this if and only if. So, and I have not written it completely. So let me erase this part. And what I want to write is if and only if there exists some channel discrimination task epsilon 0 epsilon 1. So a state does not belong to the set of these convex states if and only if there is a some channel discrimination task such that the optimal guessing probability on using this as the probe state exceeds using any of the free states as the probe state. So basically if you use the if you use this state as my probe, it will always be guaranteed that you will get a lot of success basically. Now let's try to prove this theorem in the next video.